Hello, and welcome to this presentation on trigonometric waveforms. We're going to specifically look at the sinusoidal form of y equals to a times by the sine of omega t plus or minus alpha. Trigonometric graphs are used in many areas of science and engineering for modelling natural, mechanical and electrical phenomena such as wave motion, engine reciprocation, electronic circuit characteristics, etc. Periodic trigonometric functions repeat themselves exactly after a certain time interval, and that's called the period. The sinusoidal form a sine omega t plus or minus alpha is a common periodic waveform used in mechanical and electrical electronic engineering. It's sometimes referred to as a continuous periodic waveform having no discontinuities, unlike the tangent curve which does. Analysis of situations exhibiting a regular cycle such as tidal motion, temperatures, rotation of the Earth and Sun, mechanisms moving with simple harmonic motion, can be modelled using the sine and or the cosine waveform. Thus, within engineering, it's important to have an understanding of sine and cosine waveforms and their applications. Here are some examples of systems that can be modelled using simple harmonic motion, SHM, and using the sine and cosine functions. A mass spring system, a pendulum, a reciprocating piston engine, and a cam follower. All can be modelled with trigonometric waveforms. Sinusoidal forms. A very brief recap here on how to generate a sinusoidal waveform. From previous work you've probably come across the method of projections, where we take a rotating vector, phasor, we start it with horizontal position at angle 0 and we rotate it anti-clockwise through. In this case we've shown angle omega t. We project the end of the vector across to our right hand diagram here at angle omega t and we get a point to plot. As we rotate the vector further in the anti-clockwise direction, we keep projecting the end of that vector across to the appropriate angle here, and we eventually end up with what's called a sinusoidal waveform between 0 and 360 degrees or 0 and 2 pi radians. For the purpose of this work, we're only interested in the shape, not the projection method, but method of projection is one way of generating the waveform. Let's review general sinusoidal functions. The form y is equal to a multiplied by the sine of omega t plus or minus alpha. The symbol a relates to the amplitude of the waveform, the height of the waveform. Omega relates to the angular velocity in mechanical work, sometimes termed the angular frequency in electrical work, and that's defined as 2 times pi times f, which is the frequency. Omega has the units of radians per second, rads per second. Lowercase f is the frequency, and that's defined as omega divided by 2 pi. The unit of frequency is the hertz, a cycle per second, Hz. Capital T is the periodic time, the time it takes to do one revolution or one cycle, and that's 2 pi upon omega. Unit is the second, s. Notice that frequency and periodic time are the reciprocal of each other. So if you have given the frequency, then to find the periodic time, you just invert the frequency value. And the same for periodic time. Alpha is the lead or lag angle when comparing our waveform to the basic waveform of y is equal to a sine omega t. Alpha is usually in radians, rads, in this level of work. Let's look at periodic time, capital T. If a phasor, OR, in our previous diagram on figure 1, makes one revolution, that's 360-degree movement or 2 pi radians movement, in t seconds, where the periodic time t is a time taken for one cycle to occur, then the angular velocity can be written as omega equals to the angle turned through in one revolution divided by the time taken for one revolution. So the angle turned through in one revolution in radians would be 2 pi, and the time taken for one revolution is the periodic time, capital T. It's equal to omega. So if we slightly rearrange the equation for capital T, the periodic time is equal to 2 pi over omega. And that would be in seconds. The frequency, lowercase f, is the number of cycles, complete cycles, occurring in a second. The frequency is the reciprocal of the periodic time. It's 1 over the periodic time. So if t is equal to 2 pi over omega from our previous definition, then frequency is omega over 2 pi. And frequency is in terms of hertz. We could also rearrange that for angular velocity if we wanted to. Omega is 2 pi f, radians per second. Let's define amplitude, capital A. The amplitude is the maximum or the peak value of the waveform, shown in the diagram here, the maximum height of the waveform. Both the sine theta and cos theta waves have amplitudes of unity. In other words, they oscillate between plus or minus 1. Those are the basic sine and cosine waveforms. If we're given a function such as y is equal to 4 times the sine of A, then the amplitude in this case would be 4. In other words, the waveform oscillates between plus and minus 4. The angle of lead or lag, symbol alpha. A sine or a cosine waveform may not always commence at 0. Such waveforms include functions such as y is equal to the sine of omega t plus or minus alpha, or y is equal to cos of omega t plus or minus alpha, where alpha is termed a phase displacement compared with the original equations, the original functions of y is equal to sine A or y is equal to cos A. So for example, a graph of y is equal to sine omega t plus alpha leads the basic waveform y is equal to sine omega t by the angle alpha. Similarly, a graph of y is equal to sine omega t take away alpha lags the basic waveform of y sine omega t by angle alpha. Angle omega t is usually measured in radians. So omega t is radians per second times by seconds gives you the angle of radians. A lagging waveform. Figure 2 below shows a waveform y is equal to sine A take away 60 degrees, having a 0 value and a peak value occurring 60 degrees after the y is equal to sine A basic waveform. So there's our basic waveform here. This is a basic standard sinusoidal waveform that we're looking at. And what we've got also plotted is the waveform of sine of A take away 60 degrees. This is the system waveform that we're analysing here. What we notice is that there is a lag in this case of 60 degrees between the peaks of the waveform, between the 90 and the 150 degrees. 60 degrees lag in this case. The green waveform, our system waveform, if you like, lags the basic sinusoidal form waveform, the yellow waveform, by 60 degrees. So that's a lagging waveform. A leading waveform. In figure 3, the waveform y is equal to 5 times the sine of b plus 30 degrees has a 0 value and a peak value occurring 30 degrees before the y is equal to 5 sine a waveform. So our sinusoidal waveform, I've actually just shown here the basic sinusoidal waveform, so it goes up to 1 and down to -1. Here is our system waveform, the 5 times the sine of b plus 30 degrees. This is what the system in our case is outputting. What we find here is there a lead of 30 degrees between the peak of our system waveform and the peak of our standard waveform. So this is the 30 degrees lead between the peak of the system curve and the peak of the standard sinusoidal curve. Now that often the angles used in this work are specified in radians in preference to degrees. Just be aware of that. Exercise 1 here asks us to state the unit of alpha in the equation v is equal to 150 times the sine in brackets of 20 pi t minus 0.785. From the format of v is equal to a times the sine of omega t plus or minus alpha, this is the alpha term. It's a negative term, it's a lagging term. And because there's no degree symbol, that 0.785 is actually in radians. So that's radians. Don't forget, 360 degrees is equivalent to 2 pi radians, or 180 degrees is equivalent to pi radians. So if we want to convert from theta in degrees, an angle in degrees, to theta in radians, an angle in radians, the conversion is the angle in degrees multiplied by pi divided by 180 degrees. That gives you an angle in radians. Or if you want to convert from an angle in radians to an angle in degrees, the conversion is the angle in radians times 180 divided by pi. That gives you the angle in degrees. Exercise 2 wants us to use the above conversions. First of all, to convert 1.5707 radians into degrees, and then to convert 45 degrees into radians. I'll let you attempt exercise 2 using the appropriate conversion stated above. The answers are shown on the next slide. Exercise 2 solutions here. We're asked to convert 1.5707 radians into degrees. So the conversion here is 1.5707 multiplied by 180 degrees divided by pi. That gives you 90 degrees. And we're asked to convert 45 degrees into radians. Conversion is 45 degrees multiplied by pi divided by 180. That gives you 0.7854 radians, or actually a quarter pi radians. Some calculator will give the answer in terms of pi upon 4. Example 1. A machine oscillates with the following characteristics. S is equal to 75 multiplied by the sine of 40 pi t minus 0.54, where the displacement S is in centimeters and the time little t is in seconds. We're asked to determine the following for A, the amplitude, the periodic time and the frequency, and we're asked to plot one cycle of S against t, and from the graph we plot find B, the value of displacement when the time t is equal to 0, C, the value of displacement when the time t is equal to 10 milliseconds, and part D, the time when the displacement is first a maximum. In the table on the right here, we've determined the coordinates of the waveforms. The left-hand column, time t is in seconds. In the middle column, we've got s is equal to 75 times the sine of 40 pi t. That's our basic waveform. In the right-hand column, we've got s is equal to 75 times the sine of 40 pi t. Take away 0.54. That's our system waveform. It lags the basic waveform. You then evaluate each of the rows based on the time value we're using in the equation. I'll let you do the arithmetic on that. Don't forget, when calculating the S values, make sure your calculator is in radians mode. Example 1 continued here. Below we've got a sketch of our waveforms. We've got the basic sinusoidal waveform here in yellow. This is a plot of the 75 sine 40 pi t waveform, and we can see we get a complete waveform, a complete cycle between 0 and 0.05 seconds. And we've also got a plot here of the system waveform. This is the 75 sine 40 pi t minus 0.54 radians, and again that's between 0 and 0.05. Part A wants us to find the amplitude A, and by inspection of the equation given, that's 75 centimeters. In other words, the maximum amplitude goes up to 75 and down to minus 75 on our diagram. We're asked to find the period, the periodic time, capital T, and by inspection of our graph, that's 50 milliseconds or 0.05 seconds. So from the beginning of our sinusoidal form to the end of one cycle is 0.05 seconds or 50 milliseconds. From our previous slide, we know that the frequency, lowercase f, is 1 divided by the periodic time, 1 upon the t. So 1 divided by 0.05 in this case gives us a frequency of 20 Hertz. Part B wants us to find the displacement of the system waveform at time t is equal to 0. So we're looking for the displacement of the waveform. Well, we can see here the displacement at time t is equal to 0 is minus 40. So we get minus 40 centimeters for our displacement. Part C wants us to find the displacement at the 10 millisecond mark. So that would be 0.01 seconds here, and our displacement here reads off as 50 centimeters. So plus 50 centimeters displacement at the 10 millisecond mark. And part D wants us to find the time when the displacement is first a maximum, a peak value. Now that's a bit of an estimate here. It looks like it's 0.0165 seconds, but as it's a graphical method, it's a bit difficult to tell. But that would be the peak of our system waveform, and that appears to be of that kind of estimate of 0.0165 seconds. And therein lies the problem of the graphical method from the last answer. Sometimes using the graphical method, the answers are only approximations. If we want exact solutions, exact answers, we need to look at the analytical methods of solution. And that's what we're going to do for the rest of the presentation. Solve these kind of equations, but analytically. Example 2. An alternating current is defined by the expression I is equal to 420 times by the sine of 100 pi t plus 0.32 amps. We're asked to determine the amplitude, the periodic time, the frequency, and the phase angle, stating that in degrees. Notice the alternating current waveform given to us in the question is of the form A multiplied by the sine of omega t plus or minus alpha. So the A is 420 amps. The omega in this case will be 100 pi t, because omega t is 100 pi radians per second. And then the alpha, the angle, is a lead in this case of 0.32, and of course that will be radians. So just by inspection of the equation given, knowing it's of the form a sine omega t plus or minus alpha, we can read off those values. So as we say, by inspection, by looking at the equation, the amplitude is 420 amps. We know the periodic time, capital T, is defined as 2 pi upon omega. We had that on the previous slide. So in this case, that's 2 pi divided by 100 pi for the omega. The pi's cancel, so we end up with 2 divided by 100. So that's 0.02 seconds, or we could specify that as 20 milliseconds. And we know that frequency, lowercase f, is the reciprocal of the periodic time. So 1 upon the periodic time. So 1 upon 0.02 gives us 50 hertz. Again, by inspection, the phase angle alpha is 0.32, and that's radians, and it's leading the current because it's a positive angle. We're asking the question to convert the angle to degrees, so our conversion here is 0.32 multiplied by the 180 degrees over pi, so that gives us a value of 18.3 degrees for our angle. Thus, I is equal to 420 sine omega t, 100 pi t, plus the alpha of 0.32. That system waveform leads the basic sine curve of 420 times the sine of 100 pi t by 18.3 degrees in this case. Exercise 3. An oscillating mechanism has a maximum displacement of 1.6 meters and a frequency of 60 hertz. At time t is equal to 0, the displacement is given as 800 millimeters. We're asked to express the displacement in the general form of delta is equal to a times the sine of omega t plus or minus alpha. So from the question, the amplitude a is 1.6 meters. The frequency, lowercase f, is 60 hertz. And we're given a boundary condition that at time t is equal to 0, the displacement, called that delta naught here, is 0.8 meters. That's like a boundary condition for the system. So our angular velocity, symbol omega is equal to 2 pi times the frequency from previous work we've done. So that's 2 pi in this case times by 60. So 120 pi radians per second. Often you'll find lots of answers are expressed in terms of pi because that makes them exact answers. If we start to multiply the 120 by the pi, we'll start to round up straight away with our solutions. Within this work, lots of answers are left in terms of pi, so 120 pi is a valid answer. It's the exact answer in this particular case. Exercise 3 continued here. Now we know from the previous slide that the a value, in this case the amplitude is 1.6, we got that by inspection of the equation, and the omega was 120 times pi. Now what we need to find is the angle of lag or lead, the alpha value. And that's where the boundary condition is very useful, because we were told that when t is equal to 0, the displacement is 0.8. So we can form an equation where 0.8 is on the left hand side for the displacement and the time taken is 0. So we've got all the values we need now to rearrange for alpha. So again, be careful with your transposition here. What I'm doing first of all is dividing both sides by 1.6 to get the 0.5 on the left hand side. Notice the 120 times pi times 0 is obviously 0. So that leaves me with the sine of alpha on the right hand side is equal to 0.5 on the left. Just turn the equation around here. To find alpha, we take the inverse sine of both sides of the equation. So inverse sine of 0.5, noting we must be in radians mode here. So the alpha angle comes out at 0.5236 radians. If you want that in degrees, you can convert it to degrees. It will be 30 degrees. So finally, our equation for delta in the form of a sine omega t plus or minus alpha is delta is equal to 1.6 for the A, sine of 120 pi, the omega, times t, plus in this case a 0.524 for the alpha. Exercise 4. The instantaneous value of voltage in an AC circuit at any time t in seconds is given by the expression V is equal to 34 times the sine of 5 pi t minus 0.541, that's volts. We're asked to determine A, the amplitude, the frequency, the periodic time, and the phase angle, specifying the angle in degrees. Part B, we're asked to find the value of the voltage when t is equal to 0. That's a direct solution there. We just put the value of t into the equation as given to find little v. Part C, the value of the voltage when t is equal to 200 milliseconds. And again, as for part B, we just put the value of 200 milliseconds into the equation. But of course, we must put it in terms of seconds, not milliseconds. Part D, we're now asked to find the time when the voltage first reaches 22 volts. And that's going to involve some transposition to rearrange the equation for t, and then we put the value of little v into the equation. In part E, also find the time, but this time when the voltage is a maximum. So again, that's a transposition problem. Finally, we're asked to sketch one cycle of the waveform. So from the question, the little v, the instantaneous voltage, is equal to 34 times the sine of 5 pi t minus 0.541. And that equates of the form of v is equal to a sine omega t plus or minus alpha, where the a in this particular case will be 34, the amplitude is 34. The omega, the angular velocity, angular frequency, is 5 times pi. And the alpha, it's actually a negative alpha in this case, is minus 0.541 radians. The answer to this question is given here in the brackets, and I would strongly encourage you to have an attempt at parts A to F here before reviewing the solutions on the following slides. Exercise 4 continued, part A. From the previous slide, we know the amplitude is 34 volts. The angular frequency, omega, is 5 pi radians per second. The frequency f is calculated by omega divided by 2 pi. In this case, the omega is 5 pi divided by 2 pi. That's 5 divided by 2. That's 2.5 hertz for the frequency. And we know the periodic time is the reciprocal of the frequency. So capital T is 1 divided by little f. So 1 divided by 2.5 is 0.4 seconds, or 400 milliseconds. The phase angle in this case is minus 0.541 radians, but the question wants it in degrees, so we need to convert to degrees. So minus 0.541 times by 180 degrees over pi radians gives me a value of minus 31 degrees. So that's a lag. In other words, the system curve is lagging the voltage V is equal to 34 times the sine of 5 pi t, which is the basic waveform. Exercise 4 continued. This is part B. In part B, we're asked to find the value of the voltage when time t is equal to 0, so little t is equal to 0. For this question, all we do is put the value of t into the equation as given. So from our equation, V is equal to 34 times the sine of 5 pi t, we put the t here as 0. If you now evaluate the equation, you'll get a little v value of minus 17.5 volts. Part C is similar to part B in that we've got to find the voltage, but this time when little t is equal to 200 milliseconds. And be careful with that, 200 milliseconds is actually 0.2 seconds, and that's what we should use in our equation. So we're going to let t is equal to 0.2 seconds here. So little v is equal to the 34 times the sine of 5 pi t, so the t in this case is 0.2 seconds. Take away the 0.541 in the brackets. If you do the numbers on that, you'll find that little v is 17.5 volts, positive in this case. Exercise 4 continued, part D. We're asked to calculate the time when the voltage, little v, is equal to 22 volts. So from the equation, v is equal to 34 times the sine of 5 pi t minus 0.541, all we do is put the 22 on the left hand side of the equation. We're now going to rearrange the equation to make little t the subject. So the first thing I do is divide both sides by 34. So on the left hand side I get 22 divided by 34 is equal to, on the right hand side, sine of 5 pi t minus 0.541. On the next line I take inverse sines of both sides of the equation. I've called that arc sine here, but arc sine is sine to the minus 1. And I've actually just cancelled down the 22 upon 34 here to write 11 upon 17. So on the left hand side, sine to the minus 1 of 11 divided by 17 is equal to, on the right hand side, 5 pi t minus 0.541. The sine function is gone because we've applied the inverse sine function to it. On the next line I simply add 0.541 to both sides of the equation, and I've just turned the equation around here. So on the left hand side I've got 5 pi t, on the right hand side sine to the minus 1 of 11 divided by 17 plus the 0.541. So as I said, I've added 0.541 to both sides of the equation now, just turn the equation around to swap the signs. Finally, I divide both sides by 5 pi to get t on the left hand side is equal to, on the right hand side, sine to the minus 1, 11 divided by 17 plus 0.541, and that's all divided by the 5 pi. Just be careful how you type that into your calculator. If you're using a one-line display, be very, very careful how you use your bracket. Make sure your brackets are in the right place. Evaluating the equation now using radians mode, you will get the value of t is equal to approximately 0.08 seconds or 80 milliseconds. Exercise 4 continued. This is now part E, and this is very similar to the process we used in part D. We've got to find, in this case, the time when the voltage little v is a maximum. In other words, when little v is 34 volts. So very similar process here. The only thing that's different, instead of having 22 on the left hand side, which we had in part D, we've now got the 34, the maximum voltage, on the left hand side. The rest of the solution is exactly the same as part D, so I'll let you wander through that at your leisure. What you should find is that the final value of t in this case is 0.134 seconds or 134 milliseconds. Exercise 4 continued. This is part F. Part F wanted us to sketch one cycle of the waveform. On this diagram I've actually plotted one cycle of the waveform, that being v is equal to 34 times the sine of 5 pi t minus 0.541. I plotted this against time little t on the horizontal axis here in seconds, and on the vertical axis we've got the voltage little v in volts. Note that the dashed purple waveform here over one cycle is the 34 sine of 5 pi t, and the solid blue line here is the plot of v is equal to 34 times the sine of 5 pi t minus 0.541. In other words, the blue line is lagging the purple dashed line by 0.541 radians. What we can now do with this graph is to revisit the answers we found to parts B, C, D and E and see if they actually are correct as our diagram displays them. So for part B of the exercise, we're asked to find at time t is equal to 0 what is the instantaneous voltage little v, and from our calculations we found that to be minus 17.5. If we look at the diagram, at time t is equal to 0 here, we can see that on the vertical axis the little v is down at minus 17.5, so that looks correct. Part C of the exercise said that times t is equal to 0.2 seconds, calculate the instantaneous voltage. So 0.2 seconds is over here, and if we draw a line up to our blue line here, and then we draw a line across, keeping it horizontally across, we can see that it hits the vertical axis in around about 17.5 volts. So again, that looks correct for our values. If we now look at part D of the exercise, we were given the instantaneous voltage little v as being 22 volts, and we had to find the time associated with that voltage. So on our vertical axis at 22 volts, we now draw a line horizontally across until it hits our blue curve, and then drawing a line down to hit the horizontal axis, we can see the time is 0.08 seconds, which is what we got from our calculations. Part E, we were asked to find when the instantaneous voltage little v is the maximum. In this case that would be 34 volts. So 34 volts is at the top of our curve here. So if we draw a line across till it hits the blue curve and then draw a line down, we can see it's somewhere in the region of 0.13ish. Our calculations say t was equal to 0.134 seconds. So again, that looks reasonable calculation. Exercise 4, part F. I'm just continuing part F for one more slide. What I've drawn now is the V is equal to 34 sine 5 pi t minus 0.541, but this time against angle omega t on the horizontal axis. This is angle omega t in radians. So this goes from 0 to 6.5 radians on our diagram here. What we can clearly see from this graph is that at time t is equal to 0, our basic waveform, our dashed purple waveform here, has a voltage of 0, and then 0.541 radians later, our system response also has a voltage of 0. So there's the minus 0.541 radians lag in our system. I'll leave you with some tutorial questions. They're all based around the use of the sinusoidal form of y equals a sine omega t plus or minus alpha. The answers are given in the square brackets associated with each question. Further tutorial questions here, and the bibliography, which I encourage you to review some very good textbooks here for further information. I hope this has been of interest to you, and thank you for viewing.